This video introduces the topic of rational functions and rational inequalities. The learning outcomes are to determine vertical, horizontal, and oblique asymptotes of a rational function, to solve rational equations, and to solve rational inequalities. Before solving rational problems, we will quickly review graphing rational functions to gain a better understanding of what it means to find solutions of rational equations and inequalities. When we talked about parent functions, we talked about two types of rational functions: the reciprocal function, where f of x is equal to 1 over x, and the reciprocal square function, where f of x is equal to 1 over x squared. Let's begin by graphing the function of f of x is equal to 2x plus 1 over x minus 3. First, we see that this equation does not look like one of our known rational functions. Let's use long division or synthetic division to rewrite this rational function. Now this looks like something we can graph. We need to recall the parent function graph of reciprocal function as well as our transformations. The parent function is 1 over x and has this shape. The plus 2 is the vertical shift, and the x minus 3 is a horizontal shift to the right. So our new origin is located at 3, 2, and the graph will have two branches here and here. The 7 is a vertical expansion, which means it multiplies the y values by 7. From our graph, we can see that it has a horizontal asymptote at y is equal to 2 and a vertical asymptote at x is equal to 3. We could have found these asymptotes from the equation and without graphing. We can determine asymptotes from the original equation of f of x is equal to 2x plus 1 over x minus 3. The vertical asymptote is found in the denominator of the equation. Let the denominator equal to 0, so x minus 3 is equal to 0. Solving for x, we see that x is equal to 3, our vertical asymptote. Horizontal asymptotes are related to n behaviors of rational functions. As x approaches infinity or negative infinity, the y values are approaching a particular number. This number is the horizontal asymptote. So to look at the end behavior on rational functions, we look to see how fast the x values reach infinity in the numerator and in the denominator. So we compare the degree of the numerator to the degree of the denominator. We notice that if the equation is bottom heavy, where the denominator increases faster than the numerator, the y values will approach 0 when the x values approach infinity or negative infinity. So for example, if we have f of x is equal to 2x plus 1 over x squared minus 3, we know that as x approaches infinity or negative infinity, the y value approaches 0, since the denominator contains x squared, which will be very big and definitely bigger than 2x, which is in the numerator. If the numerator and the denominator have the same degree, the values increase at the same rate. We can determine the horizontal asymptote by dividing the fraction, similar to the example that we started with. We had f of x is equal to 2x plus 1 over x minus 3, and found after long division that it is the same thing as 7 over x minus 3 plus 2, and 2 is the horizontal asymptote. If the equation is top-heavy, there is no horizontal asymptote, but there is a possibility of an oblique asymptote. An oblique asymptote is a linear asymptote where the slope is not equal to 0. If the slope is 0, then you have a horizontal line, or horizontal asymptote. So for an oblique asymptote, the degree of the numerator needs to be larger than that of the denominator, but only by 1. Thus, if the numerator has a degree of 5, then the denominator must have a degree of 4, so that the rational function can have an oblique asymptote. You can find the oblique asymptote by doing the long division or synthetic division. For example, let's say we have f of x is equal to 2x squared plus 1 over x minus 3. We see that this is top-heavy, so let's do long division. We will put 2x squared plus 0x plus 1 in the division symbol and our divisor of x minus 3 on the outside. X times 2x will give us 2x squared, so we put 2x above the 0x term. multiplying 2x times x minus 3, we get 2x squared minus 6x. We subtract by changing the sign and adding to get 6x. Bring down the 1 and see that we need to multiply by 6 to get 6x. Place the 6 above the 1, multiply 6 times x minus 3, and we get 6x minus 18. Change the sign, and add. This will give us 19 as a remainder. This means we can write 2x squared plus 1 over x minus 3 as 2x plus 6 plus 19 over x minus 3. Here we can see that the 2x plus 6 is the oblique asymptote, a linear equation. To solve rational equations, we first need to determine the domain of the functions involved in the equation. Since rational functions are guaranteed to have vertical asymptotes, we know that there will be a domain restriction, x values that make the fraction or the rational function undefined and are not part of the domain. To find the domain restriction, set all the denominators that contain x equal to 0 and solve for x. These x values are your domain restrictions. So, if we had an equation that had 3 fractions, let's say we have 2x plus 4 over x plus 2 plus 1 over x, and we have that equal to 7x plus 2 over 3. We would set the x plus 2 equal to 0 and the x equal to 0 to see that our domain restrictions in which values of x cannot be equal to negative 2 nor 0, and the domain would be from negative infinity to negative 2, union, negative 2 to 0, union, and from 0 to infinity. As with any equation having fractions, multiply all of the terms of the equation by the LCD, the least common denominator. This will result in either a linear equation or a quadratic equation. Good thing we have covered how to solve both of these types of equations. Solve the linear or quadratic equation and check your answer or answers with the domain restrictions. If your answer is in the domain, keep those answers. However, if your answer is not in the domain, omit this answer as it is not part of the solution set. To solve rational inequalities, think about how we have solved other inequalities. Find the x-intercepts, divide the number line or the x-axis into intervals, and then test x values from each interval to see if they make the original inequality true. Shade the true intervals and state your solution set. This concludes this video.